Okay, this is the last lecture hour of our course for this semester. And we will derive this Kubo formula in the BCS state by using this Nambu formulation within the BCS theory. And after we derive such a Kubo formula for this conductivity in a BCS state, you could appreciate the power of this Green's function method in condensed matter. So let's start by introducing this Nambu formulations of the BCS theory. So Nambu invented a compact notation which is based on the 2x2 matrix representation of the Green's function in the BCS state, which is given by this kind of a 2x2 matrix. And we have derived the equation motion for, say, G alpha beta, and also this F anomalous Green's functions, off-diagonal Green's function, F alpha beta. But we could combine these two Green's functions in a compact notation like this. And to do this, Nambu just define this, say, a column matrix, a row matrix, 2x1 or 1x2, given by this alpha operator, which is a column row matrix made of two operators. One is ck up, another is c dagger minus k down, which represents this kind of which is convenient to actually describe this BCS Cooper pairing. And this alpha k as function of tau is given by this column matrix. So if you dagger this, you get this column matrix like this. And then this, if you define such a alpha dagger kind of a correlation function, namely if you expand this two matrices in this product, which is what 2x1 by 1x2, right? So if you multiply this 2x1 column matrix by 1x2 row matrix, you get a 2x2 matrix, right? And which is exactly this one. And if you take this time-ordered operator and take the expression value, and with the minus sign, you get G bar, which is a Nambu formulation of the Green's function in a BCS theory. And the G bar, remember, is not the same as G, because G is simply just a one particle correlation function, okay, which is a diagonal kind of a Green's function. But G bar is defined as a 2x2 matrix where these diagonal elements are G up and G star down with a minus k. But off diagonal elements are F star down up with a k tau and F down up with a k tau. Okay, so you could combine these equation motions for G and for F that we described previously in this compact Nambu notation. So you take equation motion for this G bar, you get this equation on the right-hand side. Remember, this is simply just what we did before, nothing more than that, except we now combine the G and F in the same single equation motion for a G bar. That's all. Okay, so you take the Fourier transform from this equation motion for a G bar, you get this equation. Okay, so this is a 2x2 matrix. Again, G bar in the Fourier space is again the 2x2 matrix. On the right-hand side is a unit matrix 1. So this equation could be solved pretty easily. So the solution of G bar is this one. You simply just invert that matrix, you get this matrix. Remember, this is precisely the same form that we described earlier. Namely, this is G up, k omega, and G star down, minus k omega. Right? This is F star, k omega, down up. This is F down up, k omega. Okay, so if you compare your notes taken earlier and with that 2x2 representation of the G bar, you get a match. Okay, so we did nothing but using Nambu notation. That's all. But this will greatly simplify further calculations when we try to use both G and F for calculating these observables. So now let's just apply this Nambu notation in the problem of Cooper formula for electrical conductivity in a BCS state. So the Cooper formula is the same Cooper formula that we introduced at the very beginning of the course, which is the linear response theory. Remember, we defined this conductivity tensor sigma alpha beta in metals when we apply, say, a small external electric field, or more precisely, the external vector potential. Remember that. So for simplicity, we don't consider any external, say, potential phi here, so that gradient phi vanishes. We only consider external small vector potential A. So the small current, or called response current, in response to this small external vector potential A, is given by the paramagnetic part and the diamagnetic part. So remember, in the BCS state, we only have the diamagnetic part of this charge current, but we don't have the paramagnetic part of this electrons, strictly speaking, when t equals 0. That is precisely the London equation is telling us, right? So we have the supercurrent, which is proportional linearly to the small vector potential. And from London equation, we could derive the Meissner effect, okay? So which describes this perfect diamagnetic response in the BCS state. However, when temperature is finite, we have both contributions from the paramagnetic response current and diamagnetic part of this response. Okay, so we need to compute this electrical conductivity in the presence of both paramagnetic and diamagnetic part of the current response. Okay, so this follows exactly the same equation that we introduced in the very beginning of this course. However, the only difference is that now we are discussing this BCS state rather than this ordinary metals. So in the BCS state, we know that there will be supercurrent, and the supercurrent is made of this Cooper pair electrons, and they satisfy London equation and Meissner effect. But for ordinary metals, there's only paramagnetic part of this response current. But at finite temperature below Tc, we have both contributions. So how do we capture both contributions? Well, again, so we need this Nambu formulation of the BCS Green's function. Okay, so we can generalize this current operator in a BCS state. Remember, this paramagnetic current, the quantum mechanical formulation, is written in terms of this current operator, right? Psi dagger gradient psi in quantum mechanics. And the diamagnetic current is simply just a vector potential times the density of this Cooper pair electron charge density. So we will continue this after the short break. We could define this, say, the paramagnetic part of the current operator, and also the diamagnetic part of the operator. And then we could rewrite this current operator in terms of this G bar, or at least this current correlator, right? So the sigma alpha beta, this conductivity tensor, remember, is proportional to this pi alpha beta, right? Plus a diamagnetic contributions. But this pi alpha beta is nothing but this current correlator. Remember that, right? The J alpha, J beta are simply just this J gradient, this paramagnetic part of the current operator. So we will come back to this in just a moment. Okay, so when we calculate paramagnetic contributions to the conductivity tensor, we need the current correlator of the J gradient. What is this J gradient? Well, you can write down this operator formulation of this J gradient and this current correlator in terms of the G bar. Okay, so let's continue to reformulate this electrical conductivity in the BCS state in terms of the Nambu notation. So remember, this current response is divided into two parts. One is the paramagnetic part, another is the diamagnetic part. And the paramagnetic part is by definition following our quantum mechanics textbook, which is given by this operator, psi dagger gradient psi minus gradient psi dagger psi, right? And multiplied by this prefactor. And the diamagnetic part is simply just linearly proportional to the vector potential A times this density of electrons. Okay, so we can Fourier transform both current operators. So for the paramagnetic part, if you Fourier transform this to K space, you get this form. Okay, so we have derived the same form before, right? So when we discuss the linear response theory, we have derived the Fourier transform of this paramagnetic current operator. So the diamagnetic part is simply just this, the charge density operator, C dagger K, C, K plus Q, times this exponential factor, the Fourier phase factor, and times this vector potential. Good. So remember, when we discuss this linear response theory, and for this electrical conductivity, this response current has this relation to this linear order in this vector potential A, and times this bracket, and which we call this conductivity tensor, sigma alpha beta. So sigma alpha beta is formally defined as electrical conductivity tensor in the linear response theory, which again consists of two terms. One is the paramagnetic part of this conductivity, another is the diamagnetic part. And this paramagnetic part, pi alpha beta, is precisely this current-current correlator. We have already defined this previously. And this J alpha, J beta is precisely this part. So alpha and beta refers to this x, y, z component of this vector, k and q. So, and diagrammatically, this is nothing but this bubble diagram that we discussed earlier, right? This pi alpha beta is nothing but the particle hole bubble. But that was just for the ordinary metals. Here, we are working on the BCS state, so we need to revise and update this pi alpha beta in the BCS state. How do we generalize this? Well, you can go back to this operator format of this J, this paramagnetic part of the current response, which is given by this form, C dagger K, C, K plus Q, and multiplied by 2K plus Q, and sum over K and sigma, and divided by 2M. Okay, so this is the same as that, right? So that stuff in the Fourier space. Okay, in K space, this is this operator form of this J paramagnetic. But you could rewrite this term by dividing this upspin from the downspin component. Okay, because we know that in the BCS state, the Cooper pair is made of two electrons across the Fermi surface, right? Carrying opposite momentum and spin. Okay, so in other words, we need to take advantage of this Nambu formulation. Okay, so the downspin part is intentionally rewritten in terms of this form. Okay, so if you just go back to the original form of this spin down component, this is given by, say, C dagger K plus Q down spin and CK spin down. Don't forget there's a 2K plus Q factor, okay, which is sensitive to the sign, the plus or minus sign of this K and Q. So I can simply just rewrite this, the whole thing, 2K plus Q times C dagger K plus Q down, CK down. I can rewrite this in terms of the minus sign. Okay, so this is minus, say, 2K plus Q, C dagger minus K minus Q, C minus K down. Simply, for the downspin component, I simply just change sign of K and Q, because we know that for the Cooper pair to form, the momentum should be completely opposite to each other, right? As a result, the downspin component is written in terms of minus sign times this C dagger minus K minus Q down and C minus K down. Okay, so this is a totally equivalent to the non-flip, sign flip original form. But this kind of a new form can be fitted into the Nambu definition, because this is nothing but the matrix product between the Nambu, say, column matrix alpha dagger and alpha. right? Okay. And plus the delta Q0 right here for this. Suppose Q is 0, you get extra 1, but if Q is non-zero, you get 0. Okay, so this can be rewritten in terms of this alpha dagger alpha, with alpha as Nambu spinner, or Nambu two-component operator. And remember, this G bar is defined as this correlator of alpha alpha dagger, right? So again, this is a 2x2 matrix, right? So this is a 2x2 matrix. G star, F star, and F. Okay, so now we have successfully rewritten this operator J, this paramagnetic part in the BCS state in terms of the Nambu basis. Okay, so this is. So remember now, when we do any calculations in the BCS state regarding the electrical conductivity or resistivity, we should use this form, this Nambu formulation of this paramagnetic current operator. So now let's just plug in this J Nambu back to this pi alpha beta that I just wrote here, and in the BCS state, this current paramagnetic part of the current operator should be replaced by the Nambu version of the current operator, right? And you plug that in, and you get this. You Fourier transform this pi alpha beta, and you get this Fourier transform of the particle hole bubble, or pi alpha beta, or the paramagnetic part of the electrical conductivity tensor in terms of the Nambu Green's function. So the first two vectors are nothing but this vector k and q in this alpha component and beta components respectively. And the final vector here is a trace of this, the product of the two Nambu matrices, G bar k omega n and G bar k plus q omega n plus qn. Okay, so we need to pay attention to this matrix product. This is a 2x2x2x2 matrix product. And still, the final result is still 2x2, but you need to take the trace. Namely, you need to take the sum of the diagonal matrix elements, but you immediately recognize that both G and F, where G refers to the conventional, say, particle hole like correlation function, and F, which is off-diagonal Green's function. So both G and F play a role here, because when you take the multiplication of these two matrices, you get what? G and F star F, right? Times another 2x2, which is G prime, G star prime, and F star prime, and F prime. And you take a trace. So when you perform such a matrix product multiplication, you get what? G prime plus F star F prime, and as the first matrix element. So this is G prime plus F star F prime. And what about this second lower diagonal element, which is F star prime plus G star prime, right? And I don't care about this off-diagonal matrix element because I only need to sum over the diagonal elements, okay? So now you see the power of the Nambu formulation in the BCS state. At least at finite temperature below Tc, some of the electrons in the BCS state will get excited by the thermal excitations. Remember this gap, the BCS gap is what? 2 delta, right? This is epsilon k, this is mu, and this is E. Right? Okay. So strictly speaking, the zero temperature, all electrons form Cooper pairs, and they occupy completely the lower branch, negative branch band of this BCS Bogoliubov quasi-particle dispersion. But at finite temperature, non-zero, still the temperature is lower than Tc. So most of electrons still form Cooper pairs, but some electrons can get excited by this temperature effect or the thermal excitations. So because of the thermal excitations, some of the Cooper pair electrons are destroyed, and whenever you break one of the Cooper pair bonds, you actually release 2 electrons, right? So you have 2 free electrons released because of the thermal excitations. So whenever that happens, both G and F play the role in transport, because you have both Cooper pair electrons and also non-Cooper pair electrons, right? So whenever you have some electrons in normal states, you have, say, normal electrons. So the paramagnetic part of the current response precisely describes these normal state electrons. And those electrons are kicked off by the temperatures, and they occupy this positive branch of this Bogoliubov band. Okay, so those electrons in normal state, they should satisfy all this paramagnetic kind of a response function, and so we should describe this normal state electrons by this paramagnetic part of the current. However, we should remember that many of these electrons are still in this lower band, namely the Cooper pairing states, so that those electrons are sort of connected to the Cooper pair states. Okay, so as a result, even at the finite temperatures, when temperatures below Tc, both G and F are involved when you calculate the paramagnetic part of the response, because those electrons come from this Cooper pair state. Okay, they sort of kind of link to all the other electrons in the Cooper pair state. Okay, so of course they sort of free electrons, but they're not so free, because you know very well that those electrons are not described just by the G, but F also contribute. Okay, and so that is what we should do in finite temperature, but T below Tc. Now this electrical conductivity can be computed in the Nambu formulation of the BCS Green's function. Okay, so you can imagine that if you don't introduce such a Green's function G and F, how do you calculate this electrical conductivity in the system where some of the electrons are still in the BCS state, but the other electrons already are in excited states? So this mix between this BCS ground state and this Bogoliubov excitation electrons, so really messy if you don't introduce this very elegant Nambu formulation. Okay, so this is the end of our semester's course, because the remaining job is to evaluate this thing. Okay, so you could straightforwardly follow all the derivations described in our textbooks. So like this formulation, so you can imagine that there are many other quantities in the BCS state at finite temperatures that could be computed by this kind of Nambu formulation. For example, this spin susceptibility, for example, magnetic susceptibility, or structure factors by neutron scattering. And whatever you want to measure in the BCS state at finite temperatures, they are related to both G and F Green's functions. Okay, and this is the most, I think this is probably the only way that you could perform such a calculation. And once you take the trace of this matrix product and you sum over Matsubarra frequency and momentum, you get pi alpha beta as function of a Q and Matsubarra frequency, and you could analytically continue in this to this real frequency, and this is nothing but AC conductivity, right? This is sigma alpha beta k and omega. This is the AC conductivity. And you know very well that you can measure the AC conductivity for materials, including superconductors. So you simply just apply an AC field, the AC electric field or AC magnetic field in your system, and you calculate this transport as function of momentum and frequency. Okay? But theoretically, how do you get this? Well, this is the way that you can get. And neutron scattering, what you will observe is the spin structure factor, which is related to the spin-spin correlation function. Again, the spin-spin correlation function in the BCS state could be reformulated in terms of Nambu matrix, because the spin in the second quantized language is described by what? Right? Sigma is the Pauli matrix, and F is fermion operator, right? Okay. So if this F is just our BCS Cooper pair electrons, then this Si Sj correlator is what? Something like this, right? Sigma prime. Take a dot product. Okay, so you get all sort of correlation function related to this C dagger, but C dagger is not a good basis in the BCS state, right? So you need to transform this to this Nambu basis. And as usual, you could imagine that this both G and F Green's functions involved in this spin-spin correlation function. So once you have derived this G and F and you formulate all these observables in terms of Nambu basis, then you are done in principle. Well, of course, the calculations are not easy because you will hit this gap and the pole and you need to sum over this momentum, and so it's not so easy task, but it is possible. Okay, so I guess that's probably everything I need to tell you. But of course, in BCS theory, you have this gauge symmetry, right? The U1 gauge transformation and things like that. In the BCS state, it breaks the global U1 gauge symmetry because of this Cooper pairing. Okay, if you write down this BCS mean field Hamiltonian, and the U1 gauge symmetry is broken, okay? But you could read this part of this section in our textbook. Okay, so to summarize the whole semester's course, so we introduce this Green's function, correlation function, and then we could use this perturbative expansions and Feynman rules, Feynman diagram methods to compute this Green's function in K and omega space. And then we could use this information to calculate any observables that you can measure in laboratories. Okay, so this is the purpose of our course. I hope you could benefit from these discussions. And we have given you examples of well-known condensed matter systems such as Anderson localization disorder impurity problems, and also Coulomb interacting electron gas, electron phonon interactions, and the BCS theory of the superconductors. So this encompasses pretty much everything that you can find in ordinary solid-state physics, but we use very powerful mathematical tools, which is the Green's function method, and is very general, and can be widely applied to all the systems that you can imagine. So the final word is that Green's function, from theoretical point of view, is everything that we need to know in condensed matter. Okay, so once we know the Green's function, both the real and imaginary part, and we pretty much know everything about the materials, so the Green's function is really the key from theoretical perspectives in understanding in condensed matter physics. Okay, so with that, I thank you for participation and listening and studying this course. Thank you very much again.